I'm done. Enjoy.
I'm on the hot seat. Okay. All right, guys, we're going to be going over troubleshooting. Now, the way I like to tackle these things is I'm sort of a big believer in kind of feed a man a fish. You feed him for a day and give him a fishing rod, and you feed him for life. So what we're going to go over first is actually how all the different sensors and the different types of sensors on the boiler work. Some of them are fairly basic, some of them are a little bit more complicated, but once you know how they work, hopefully it makes it a bit easier to troubleshoot. Okay, so we'll start off just a quick sequence of operation. We're going to go through understanding different types of sensors, switches, how the blower is controlled, how flame signal works. We're actually not covering negative pressure regulated gas valves. I did that 2 or 3 episodes ago, so if you haven't seen that, you can go look it up. As for maintenance, I actually just didn't update the presentation title, so we're not doing that tonight either. So sequence of operation, first thing you need to do on any time you do a troubleshooting is you need to understand what should be happening before you decide what's wrong. We run into this a lot with new tech support guys and people that are new to the product. They have it in their head what they think should happen, and it's not really what you think that matters, it's what the boiler thinks. So before you go in and start troubleshooting, make sure you understand a few things. Where does your call for heat come from? Do you have outdoor sensors? Do you have system sensors? Is the boiler part of a cascade? Did the problem start, recently? Did it start 6 months ago? These little things, they're all clues. You've got to be a bit like Sherlock Holmes. You don't know what the problem is when you get there, but you've got to rule out what's not wrong until you find what is wrong.
Dave, I like the question. Right. I love to ask, did it work when you put it in?
Yeah. Yeah, did it work when you put it in? Exactly.
Pretty easy. I mean, did it keep up with the domestic hot water 3 years ago, or didn't it? Right now we can troubleshoot.
Exactly, and specifically, and there's a couple of things that go along with that, like hot water problems. If it's a lack of hot water, if it's from day one, it could be that it's just undersized, especially if it's a combi. But if it's something that developed over time and has gradually gotten worse, then you're looking for perhaps a different set of symptoms or different set of problems. Every boiler ever made goes through a decision before it decides to fire the burner. So the first thing the boiler has to do is decide, should it do anything? You've asked it for heat via your jumper wire for thermostat or jumper wire for hot water or tank sensor or aquastat, whatever it is you're using. So the boiler is then going to look at its outlet temperature versus the active set point. And keep in mind, guys, especially with these newer boilers, the active set point, you could have up to 4 or 5 active set points on the boiler, or I should say you can only have 1 active set point, but you could have 4 or 5 total set points. So you need to be 100% sure you know which one the boiler is responding to, because if it's responding to a call for heat that requires 80 Fahrenheit, and you're expecting it to call for heat and you want 180, you're going to be disappointed. So your outdoor sensor affects your active set point in most cases. Warm weather shutdown, this one caught me this past winter. I spent probably 30 minutes troubleshooting before I realized that they had enabled a warm weather shutdown, and just one of those things, you get tunnel vision, you think there's a problem, and of course it just turns out the boiler did exactly what we told it. Another good practice to get into, go through all the inputs and outputs on the boiler. So you want to look at inlet temperature, outlet temperature, stack temperature. If you have a flow sensor on the boiler, check to see the status of it, assuming it's something you can see. And make sure these things seem like they're reasonable. Touch the pipes, stick your flue analyzer in the flue test port and see if the flue temperature seems reasonable. Sometimes the answer is really simple. The boiler's just got a bad sensor or bad wire harness, and it gets overlooked because it maybe isn't bad enough to give you an error code, but it is enough to stop the boiler from functioning. Make sure you do, again, no competing calls, because a competing call could override the one that you're expecting to have happen. And then safety's in the proper configuration. Hopefully they're in the proper configuration when you get the boiler, but there are, of course, times when you add safeties because the inspector or the job requires them. So make sure that they're set up properly. If you have external safeties, one of the easiest things to do is just to bypass them. If your problems all go away as soon as you do that, probably a good bet that there's something wrong with those external safeties, whether they're doing their job or not. Okay, so once we've decided that the boiler or the burner wants to come on, so we've got a call for heat that comes in from your thermostat. This is the Honeywell T87K here. And bear with me a moment, I'm using the trackpad on my laptop and struggling. Oh, wrong way. Okay, there we go. So we got our call for heat coming to the boiler. What I recommend, I'm a big fan of jumper wires. So in a lot of cases, when I'm troubleshooting with you guys on the phone, I'll tell you to take the thermostat off and just use a jumper wire, because I know exactly what that does when you're using it. Not always sure what the thermostats are doing. We're then going to look at any internal safeties. So I've picked sort of representative safeties for this product. So there's a low water cutoff, there's a blocked condensate switch, and basically the power for these for the gas valve actually passes through those devices. And then we have an auxiliary limit, and these are things that you would wire external to the boiler, and they're going to go back to the low voltage terminal strip. So roughly speaking, your wires are going to come from the control and go back to the control for the internal limits, provided we have continuity through these. We're then going to check any external safeties that might be wired on the auxiliary limit circuit. And once this is all verified and the inlet outlet stack temperature are all within range, the boiler is then safe to proceed to the next step. So the next step is we're going to continuously monitor both the thermostat and the internal safeties. Then we send a signal to the blower, and the blower sends a signal back to us. If we don't get that signal, we don't light. If we're happy with the blower signal, we power the spark transformer, which hopefully causes spark to occur. Then we add gas, and the timing for this, it's fairly consistent across all the boilers that we've made since I've worked with NTI. So roughly speaking, you're going to get, I'm going to say, about 7 seconds worth of spark. And the last 5 of those seconds, so seconds 1 and 2, it's spark only or hot surface only. And then seconds 3, 4, 5, 6, 7 is going to be gas and spark, or gas and hot surface at the same time. And if everything goes well and everything's working, we're going to get a flame in the chamber. And we're also waiting for the flame signal to come back to the boiler control. One thing that sometimes throws people off is they'll look and they'll see a flame, but they sort of forget that the boiler needs to see that flame as well. And you've got to remember that that flame rod is the boiler's eyes. It's not as bright as you are, so it can't see the flame except for the flame rod. Okay, so now we've gone over the basics of how the boiler decides to fire. We're going to go through some basics on switches, and some of this is a bit simplistic. I hope for you guys there's some value in it, but there's 2 common types of switches. Normally open, normally closed. There's each switch is shown in its status, or its normal state, meaning when you're sitting there and you haven't provided the conditions that should trigger it, whether that's a low water cutoff, whether it's an air switch, whether it's a pressure switch, whatever it happens to be. This is the state that the switch sits in when you sit it on the desk in front of you. So normally open means the contacts they're not connecting a circuit, and normally closed is just the opposite. And once I activate this circuit, you can see that they switch positions. So a normally open switch closes as soon as the triggering condition is met, and a normally closed switch will open or break the circuit when the triggering condition is met. Now, so we're going to go to our first poll question. And the question to you guys is, the low water cutoff in the TFTN or TFT, or really any low water cutoff, is it a normally open or is it a normally closed switch? So pick your answers and we'll move forward from there.
There we go, folks. The poll is open. So is the boiler low water cutoff normally open or a normally closed switch? Your choices are normally open, normally closed, or yes or no. Not sure what yes or no mean, but normally open or normally closed, or yes or no. So
sorry guys, yeah.
Submit your questions. Don't worry, Dave. I mirror imaged you on what you had, but I also added normally open,
normally closed is winning.
Yes, it is. Normally closed is rocking and rolling.
But 1/3 of our participants have not voted.
Wow. Come on, folks.
Okay,
Get
you
your answers in
lagging
there.
third. Let's get in here.
They're not sure what a normally open, normally closed is. So, I guess. Wow. So 27% so far. I think you can see that Dave say normally open. 73% are saying normally closed.
Okay. And has everybody voted? 83% voted.
Yep.
All right, we'll
So
give you guys another 10 seconds.
9, 8, 7, 6, 5, 4, 3. 17% have no effing clue. So I'm going to close that, and you know that 73% said normally closed, 27% said normally open. I'm going to close that poll. There we go. And you're
Perfect.
back to your poll question sheet up.
So although the low water cutoff should remain closed anytime the boiler's opening, it's actually a normally open switch. The standalone condition of this switch, if you just sit it on your desk, when there's no water touching it, is in the open condition. It does not make the contact, and it's adding water that creates the contact. So although the switch itself is, generally speaking, remains closed for the life of the boiler, the switch's natural standalone position is actually open. So it's a normally open switch that closes upon the addition of water.
Good question.
Now I have to. That is a good question, because think about
Well,
this. For
It is. What does the switch do when you set it on your desk in front of you? Is kind of how I look at it.
Well, think of this. You know, for all those years, we told everybody not to put Teflon tape around the brass probes, because the brass probe with low water cutoff allows continuity to be sensed back too. So
Yeah,
you
we're going to
get
go
issues.
over later in the presentation here. We're actually going to go over
I'm
how
sorry.
low water cutoff works, or at least the one that we use. So, all right, guys. So, where are some normally open switches that NTI uses in its various products? Well, we use
Oh my God. David, you have some historical pictures here.
I do.
Sorry, go ahead. I apologize.
No worries. So we've got the Nason water pressure switch. It's a normally open switch that closes with the addition of enough pressure. Now we do call that a water pressure switch, but in reality, it's just pressure, and we'll talk about that in a second. We've got the old TI flow switch, the GEMS FS380 there. We have the Huba air switch, which technically is not a normally open switch, but we often use it in the normally open position, and we'll make reference to that as well. The trusty old safeguard cutoff.
You actually pronounce that Huba? It's not Hubba?
Huba or Hubba or Huba. I don't know.
I've been calling it a Hubba
Like
switch
Taylor,
forever.
I don't know.
No,
How do you guys call it?
I will now call it a Huba switch.
Huba sounds better. It's like, I don't go to
sounds
I don't go to Target. I go to Target. So there's the safeguard low water cutoff, and of course the gas pressure switch there, which is commonly used on the FTGs and the new TFTN 500 and up series, actually come with those switches built into them. So these switches all remain sort of in the open position until something triggers them to close, and we'll talk about that in just a second. So there's our switches closing, and we're on to the next slide. So the other set of switches we use, and you'll notice that there's two duplicates from the previous slide, are the Huba or Hubba air switch. We have a different type of air switch there from, I can't remember who makes that one, but anyways, it is another air switch, the big silver one here. This is an old product from the Matrix. For any of you that remember that, we had a freeze stat to prevent the coil in the top freezing. So it was a normally closed switch that opens upon temperature drop. So if it gets too cold, it opens a circuit. Down in the bottom of the screen here, we've got a newer addition to some of the products. So for those of you that do LXs, you will have seen some of these on the burner doors. This was recently added to the FTVN boilers, and it's attached to the burner door as well. And it's a high temperature manual reset thermal limit. And again, it is a normally closed, and it opens upon temperature rise. So if it gets too hot, it opens.
David, is
Yes.
that also on the TFTNs?
Yes, it would be on the TFTN 199 and down. And I'm trying to think, it I don't remember if it's on the bigger ones. I'd have to look.
It is. Yeah, it is.
Is it on the bigger ones? Okay.
Yeah, because I was looking at that today, 285.
I think it's not on the ones that I have in my training room in St. John because I sort of got the prototype. So, but yeah, for production, yeah, it probably is there.
And that was there for safety, for safety, right, Dave? That's why I had to change it.
Well, yeah, no, the reason it's there is in some cases, if the boiler is reassembled incorrectly, if the gasket or a gasket fails or the burner door refractory fails, the burner door can become effectively red hot. And this switch is designed to prevent any serious damage if that does occur. So one thing I will say, guys, is if you do see these thermal limits tripping, although they are resettable, they're a bit like the airbags in your car. It's probably more than just a minor fender bender that caused it to trip. It is a pretty serious indication if you see a thermal limit trip. So watch out for that. It's not just, oh, I'll reset it and get back to it next week. It probably should be addressed right away.
No, it's good you brought this up because that's something new to the TFTN that guys are seeing. So
the
Yes.
case I had where the entire heat exchanger inside was full of calcium and the supply return sensor could not sense the temperature. So the burner kept on firing because it couldn't get to 180 and it started to melt the door. Now this will turn it off.
stop it. Yep.
Absolutely. And, back in the day with the old TI series, I actually did see a couple of burner doors melt off of boilers for similar type of situations. The heat exchanger was in, catastrophically bad maintenance, and the burner is hot enough to melt everything the boiler is made of, with the exception of those white refractories. Everything else, it's plenty hot enough to burn them if it's doesn't have water cooling it off.
That had to be pretty hot.
Oh yeah,
Well,
yeah.
Used
So
to be able to
this
jump
is
out the
a
sensors.
this is a cutaway of, this would be representative of the Nason water pressure switch that's on all of our LX and the TI boilers. And the way this guy works basically is there's a rubber diaphragm in the middle here. And what happens is when water enters through the hole in the bottom, it will push on the diaphragm. And when it does that, it literally just activates a set of contacts. The little spring is in there. So there's our electricity coming through. It can't pass through until we add some water pressure. Once we add sufficient water pressure, basically you close the switch and compress the spring. Now these are adjustable, but because I'm not the best artist in the world, I didn't draw the adjustment screw, but you can imagine an adjustment screw tensioning that spring at the top. Those are factory set. They're not intended to be played with in the field. So oftentimes that switch is epoxy closed when you get it, but they actually do have an adjustment on them as well. And that's what happens when you get enough water pressure, it will trip the switch. You can actually fake these switches into tripping. If you take a small rod and push it up inside the switch, you can activate the switch as well. They're just a physical rubber diaphragm. The contact gets closed by the diaphragm deforming and compressing the spring, and then it allows electricity to pass through. Now, of course, if you lose pressure, the spring will push the diaphragm back open, opening the circuit, and whatever safety is getting power from that stops getting power. So that's the water pressure switch. And again, they do come in, the ones that we use are all normally open switches and they close upon pressure rise. If you have a TX, it's one case I actually didn't put the sensor in here. It's a different type. It's more of a pressure transducer, which this presentation doesn't cover, but the majority of what we use is a switch like this. This actually would be also representative of the switches on the FTVN and TRX.
Hey, Dave, can
Yes.
that be bypassed manually just by jumping out the two wires to see if it's the switch or not?
Yes, anything that happens to be a switch, you can basically, if you take your jumper wire, and again, I love jumper wires, and you just connect the two blue dots together with your alligator clips. If it's a switch, you can jump it out. If you're not sure it's a switch, make sure you talk to somebody first, because there are certain sensors that if you jump them out by mistake, you'll actually fry the control board. Most of the time, it won't do any damage, but there are a few rare cases where jumping the wrong thing fries the board. So if it says switch in the instructions or in the parts breakdown, you're probably safe to jump it, I would say 99% of the time. Okay, so this switch, it's used on, it's also used on the old TS80. So for any of you guys that have some legacy products out there, the TS80 also uses this water pressure switch. Air pressure switches, air proving switches, air switches. We actually call these a couple of different things. We're going to treat them separately for now. So this is your basic air switch. Again, it's got a rubber diaphragm in the middle. It's got a set of switch contacts at the top or the bottom. There's actually a spring in there as well. And the way these guys are intended to work is if you get enough suction on the top port or enough pressure on the bottom port, you activate the switch. So if we suck on the top, electricity passes through. If you were to have a single tube hooked up to your air switch, like the old T series, for anybody that's been around that long, we used to use a single tube on that air switch, and we actually didn't use the suction. What we did on that guy was we used the positive pressure that came off the blower, and it would blow into the one side of the switch, and it would trigger the switch to activate and allow the boiler, the Sentry in this case, to fire the burner. Of course, if you create suction on what should be the positive side or create positive pressure on what should be the negative side, the switch will do the opposite. Now, we don't always use the ports as you might expect. We use them in different ways depending on the product, and we'll hopefully cover that a little bit more. Now, one thing that you want to keep in mind with these is the pressure difference between the top and bottom is really what's tripping the switch. It's in a lot of cases, we don't use just one or the other port, we use both. And when we use both, it means that this is a pressure differential switch. So it's a bit like taking a static pressure with your manometer and use a differential pressure manometer, and you go to two different points in the ductwork and you get a static reading. That's kind of how we use these switches in a lot of cases, is it reads an intake and an exhaust. And obviously there's always a bit of positive pressure in the exhaust and a bit of negative in the intake. But if either one gets too far out of range, it can trip the switch. So look at where the tubes run. And we're going to talk about a special case where we use this as an air flow proving switch in a few minutes. So again, same thing, you blow into the bottom, it'll trip the switch. If you blow into the top, you deactivate the switch. And when it's used in the dual port configuration, if you provide equal pressure, top and bottom, whether it's suction or pressure, the switch does nothing because the pressure difference between top and bottom is 0, which means the diaphragm sees no net movement one way or the other, and the switch will remain and not do anything. So anytime you see two ports connected on that switch, the intention is that both ports might be negative, they both might be positive, but while the boiler is doing something, there will be a difference between them, and either that difference needs to be great enough to trip the switch, or it needs to be not great enough to trip the switch, depending on the application. So this is creating pressure differential using the air proving switch. Now, we still do this on the LX products. So if it's got a white Huba switch like this, it actually gets tripped by creating a pressure difference. So what I've represented here is an air intake pipe with two pressure tappings. The little blue lines in these pressure tappings are supposed to represent pressure. So what's going to happen is at some point your blower is going to kick on, and when it does that, it's going to drop the pressure in the intake pipe, and both pressure tappings are going to see a decrease in pressure. Just like water flowing through a pipe where you get head loss and friction loss, the pitot tube, or the tube that's downstream of the flow, should see a little bit more pressure loss than the tube that's upstream. But if you've worked with any of our products, you'll notice that these two tubes are literally 6 inches apart, or not. Sometimes they're only 2 inches apart. And so the pressure difference between those would effectively be 0. It would be a very, very tiny amount of pressure difference. So the way we get around that, and the way we're able to use this as an air proving switch, is we actually place an artificial restriction in the intake pipe. So we're going to run our tubes first. There's our air tubing connected. And these two little blue blocks in the middle here, that creates an artificial restriction. And just like if you've ever washed your car with a garden hose and you're going around the back of the hose and you start tugging on it, all of a sudden it kinks. Anything after the kink loses water pressure. Well, the same thing happens when air flows through this pipe. And if I can get my slide to work for me. There we go. So we've got our air coming through. After we pass through the restriction, you can see that on the right-hand side, we've dropped and lost a lot more pressure than we did on the left-hand side. And that's because this restriction creates a drop in pressure. Now, the reason we do this is if we only used a single tube, it just tells us that there was a pressure drop and it doesn't tell us whether there was flow. By using two pressure tappings in the same pipe and creating an artificial restriction in the middle, it allows us to characterize the airflow through that intake pipe or exhaust pipe, as the case may be. And we can then set the switch to a reading. So the old TI switches were always set at 2/10 of an inch water column or 0.2 inches water column. And when everything was working right, that meant you had enough air moving in order to create the correct pressure difference to run the burner safely. So when the air stops, the pressure drops or increases to a normal reading because when you're not sucking on the pipe, of course, the pressure is going to go back up again. And that means we have no water or no airflow. We also use these switches, the same exact switch, but a different application. And we use it as a normally closed blocked vent switch. So these are used on LX boilers. Also on the LX, it's the big silver switch. On the TFT, TFTN, the TRX Series 2 and FDG products, we use this as a condensate blocked exhaust switch. And the way it works is fairly simple. Again, we allow power to pass through a set of normally closed contacts this time. And as long as everybody's happy and we've got good flow, we see a small pressure change on the one tube and the switch allows power to pass. However, our favorite little mouse with the cheese gets in the exhaust and dies. And what's going to happen is he's going to create an artificial restriction. It's going to increase the pressure, getting above the set point of the switch and shutting it off. And of course, what's going to happen there is the boiler's going to shut down. So now we're on to normally open, normally closed switches. So this is a very rough wiring diagram of what these switches look like inside, electrically speaking. So you can see the Huba switch there, and all the Huba switches have three contacts. We use them sometimes as a normally open, sometimes we use them as a normally closed. When you have a dual purpose switch like that, it means that one set of contacts, so the ones that are highlighted, are closed until the switch is tripped, and the other set are open until the switch is tripped. So this is a oh, sorry.
I said, Dave, hanging on my wall in my office is a picture of the TI boiler and the wiring, because people always switch the wires between the normally open, normally closed when they reinstall it after they take it apart. And
yep.
And I literally have it there. So somebody says, well, where does the white wire go? I have it hanging on my goddamn wall.
Yep, I had my own little script in my head. It's okay. It's the two wires closest to where the tubing connects to the air switch. Just use those two. The third one, ignore it. Now we've gotten a little brighter in our old age, Steve, and on a lot of the new boilers, if there's an unused terminal, we've tried to make our techs' lives easier by unscrewing that terminal so that it's just not an option. But with the old TIs, we just left it as it was, so it did confuse some people. So yeah, now if we trigger this switch, so let's do that. It kind of does what you might expect, which is you're going to open the normally closed contact and you're going to close the normally open contact. I guess in theory, you could take power away from something and apply it to something else, but typically these switches are not used in that fashion. Usually just one thing occurs. And what you want to do is, to Steve's point, if you look at the face of these switches, so if you guys look right embossed into the plastic on the face of this, or embossed into the plastic on the face of this Honeywell switch on the right-hand side here, there's actually a wiring diagram in there, and it'll say NO, NC, and C. C stands for the common, which means that it's the one that connects to one of the other two. And then the normally open is the one that's going to close, and the normally closed is the one that's going to open. So, but always keep an eye out for those diagrams, because they typically are there on anything that's a dual acting switch like this. There we go. We'll switch our switch back again. And now we're going to talk about our high gas pressure switch. So we have two different types of gas pressure switches, and these are commonly used on like FTGs, TFTN 500s, 800s, that kind of thing. So the high gas pressure switch actually mounts in a location where it sees the gas pressure leaving the valve and entering the combustion blower fan, or entering into the back of the gas valve. Sorry, no, entering into the blower, I guess. So it sits between the gas valve and the blower, or between the gas valve and the venturi. And the idea behind this switch is that if that pressure ever gets too great, meaning that somehow the valve is passing too much fuel, it will trip the switch. Now, in reality, with a negative pressure regulated gas valve like the one that we use, and the setting that's used on that switch, they will never trip under any condition that I can think of, except for some sort of backfire event on your boiler. So if your boiler has a very rough ignition, it can create a pressure pulse that's strong enough to come back and trip a high gas pressure switch. But in virtually any other case, there's really nothing that should trip it. It just shouldn't. It's almost impossible for that to occur. So unless you're really, really unlucky, you're just never going to see that. The low gas pressure switch, you're probably going to have to reset this, and it's probably going to trip every single time you do a startup. And that's because it goes on the gas line that feeds the boiler. And if we don't supply enough gas to feed the boiler, it trips out. And the reason that you're probably going to see it trip on just about every job is at some point you're going to be working, somebody's going to shut the gas off, or the inspector's going to shut it off. You're going to trip the switch. These ones are manual reset, so you do have to press the little button to reset them. So if you're doing a commercial boiler job and you start getting gas pressure switch errors, I'd say dollars to donuts, going to be the low pressure switch, and you just have to reset it and ensure that you've got good gas pressure, and your problem should go away. So again, these switches they are normally open, normally closed. We only use 2 wires on them, and we wire them as both normally open and normally closed, depending on where it mounts within the boiler. So there's our low gas pressure switch, which is typically a normally open, and the high pressure switch is typically a normally closed. I actually asked engineering, is there a particular preference for when you'd use high and low gas pressure, or sorry, when you'd use normally open versus normally closed? And really the answer is it just depends what the controller that the boiler is working with likes. So if the controller wants to lose power to something, then we would use a normally closed. And if we want, for example, to send power to something, then we would typically use a normally open contact. And so there's no rule for when you're going to see one or the other. It's application specific. Look at the wiring on the switch. It should tell you what it is. Now we're going to get into something called a Hall effect sensor. These are used very frequently in the big bad world. And the way these work is you have some sort of magnetic device, typically that rotates. So this could be like a wheel speed sensor for a car. It could be in a combustion fan motor. It could be in a flow sensor. And every time this magnetic pole sweeps past the sensing element, typically you're going to have a low voltage, like 5 volts. And so 5 volts comes in, the little device is grounded somewhere, and then you get a dashed or a pulsed signal going out. The controller can count those pulses, and basically based on the number of pulses, it knows how fast something is moving, or how much water you're using, or if it's a car, for example, how fast you're going. So fairly simple devices, unfortunately not the easiest things to test when we're in the field, because our voltmeters just aren't set up to read that pulsed signal coming out of them. But they should have some sort of low voltage going into them. Typically there's a ground pin, and don't take this picture as a hard and fast rule for what it's going to look like. Typically they don't look like anything because the sensing element is embedded somewhere. So we're going to show you a real example here in a second. So, poll question, where are Hall effect sensors used? So the options are, as it relates to boilers, flow switches, flow sensors, air switches, pressure sensors. So where would you see a Hall effect sensor in a boiler?
And Ted, I think you can see the responses, so I'll let you go for it.
40 and 50% have voted. The majority at this point is saying flow sensor. We have 40 seconds into the poll. 70% have voted. We have not yet gotten to the 86% we achieved previously.
20 seconds, guys.
Get your votes in.
10 more seconds. 9, 8, 7, 6, 5,
This
4,
is true.
3, 2, 1, done. Okay, so we got 80% participation. Okay, so flow switches was 13%. The correct answer is 69% for flow sensors. For the people that said flow switches, you may be thrown off by the magnet, and in a flow switch, there typically is a magnet, but it's used in a different way. So we're going to talk about that in just a second. There are no magnets in air switches typically, and typically there's no rotating component, although it's possible that you could use a Hall effect sensor to measure flow, airflow, for example, using one of those, oh, help me out, Ted, here. What are those things? Anemometers, the ones you stick in the airflow and it spins the little blade. I'd be willing to bet that any digital version of that has a Hall effect sensor in it. Okay, so here's a TRX. So this would be TRX 199 or any of the FTVN combis. I specify TRX 199 because the 150 TRX does use a different device, so don't confuse the two. Basically, embedded in this are two little magnets, and somewhere in here, there's a little magnetic pickup, and every time those two magnets pass over the magnetic pickup, a pulse is sent to the controller counts the pulses, and somebody who's gone through and done the math and said, well, each of these veins carry whatever, 2 milliliters of water or 2 ounces of water. Based on how many times it spins per second, we can determine how many gallons per minute are flowing to the fixture. The other pieces you see in the photo here, this little horseshoe-shaped clip is what holds this whole assembly into the boiler. So if you have not had to disassemble one, off on the right here, you can see the housing. So the brass housing is literally just a housing. It has no particular, doesn't do much for the operation of the switch. It really is just there to hold it together. It does contain this little filter. So you can see the holes in the filter, and the filter actually is important to the functioning of this because this guy has to spin on this little pointed bit at the top here. The filter not only keeps big debris from getting in, but it also directs the water flow to one specific side of this, which means that it wants to spin in a particular direction. If your filter is missing or damaged, sometimes these little mounting tabs will break off and that thing will rotate in its housing. Typically after it's been disassembled once, so when you reassemble it, just use care that the little these little latching clips go back where they're supposed to go. There's little divots for them in the brass. But if this thing rotates or gets plugged up enough, of course, this stops spinning. The other thing we've seen is there's a little plastic point on the tip of this. Typically in cases where there's a recirculation line that's probably running 24/7, we see that this little pointed tip gets worn off and it becomes kind of flat and dull. And when that happens, the flow meter, there's too much friction inside and it just doesn't spin very well. And because it's not spinning, you get intermittent hot water calls or no hot water calls.
You know, it's funny you say that. That's recently come up, Dave, with the recirculation loops.
Yeah, we put out a bulletin about it because we were noticing in tech support that every time someone called with a recirc, that the flow meter was wearing out prematurely. So if you do use a flow meter, guys, put a timer on it, put a temperature activation on it, but preferably don't run it 24/7. And if you do, you probably are going to end up having to replace that every couple of years.
Well, yeah, I just don't understand why somebody would put a domestic hot water recirculation line on running 24/7 when there's so many things, timers, aquastats. I mean, good golly, why wouldn't you do that?
Well, it doesn't make any sense because they're constantly running flow through there. I mean, doesn't make any sense.
The only thing it guarantees is that you have hot water at the taps at all times. But just to give you guys an idea, if anybody out there sort of thinks that maybe it's still not a terrible idea, I did the math for a house that I'm building, and I believe that the recirc line, if I left it running 24/7 based on the heat dispersion from 1/2-inch PEX, it would burn somewhere in the region of 1 liter of propane per day worth of heat loss. So for those of you in the States, which is all of you, about just under 1/3 of a gallon. So it take every sort of 3.5 days, I would burn through a gallon of propane just to keep a recirculation line hot. So it wastes a fair bit of energy.
So
There
in
you
a
go.
month, you go through 10 gallons of propane just for your circulation line, doing nothing else.
Waste the fuel.
Exactly. And if you insulate the line, you'll burn about half that. And if you insulate it and put a timer on it so that it's a timer and a temperature sensor, you can probably cut that to, a gallon every 2 or 3 months, which is what I'll be doing. I'll be putting the insulation on, and I'll also be putting a timer on it because I work for NTI and I know a guy that can get me one. So.
Well, you're gonna do it. You're gonna do it right too. On top of it all, I mean, that's
We'll do our best. So Hall effect sensors, we also use them in our blowers, and this is going to kind of deviate somewhat from the sensor in as much as we're going to talk a little bit about how the blower works as well. So all of our blowers, and I had to use a blue wire here because basically the white wire on the white screen just doesn't show up. So in the field, that would probably be a white wire for you guys where it says 0 to 30 volts DC. But the colors are kind of irrelevant for the explanation. The way your blower works is it has a feedback line. It's got a ground line so that the electronics inside it know how to work. You've got a voltage signal, sort of voltage hot, so in this case 30 volts DC, and then you've got a variable voltage, so 0 to 30 volts coming in that controls the speed of the blower. Up on the right here, I've given you a little bit of a cheat sheet to say, TI series boilers, the blowers are controlled with 0 to 35 volts. TRX FTVN, it's 0 to 24 volts. TFT LX FTG boilers, anything using a SOLA control. So if we have any Lars fans out there and you've got a SOLA, it's 0 to 30 volts is the control signal. And what your blower does is it looks at this 30 volts and it compares it to the secondary voltage, the variable. And the difference between the two drives the fan. So if the difference between 30 volts and 15 volts, let's say, is 15 volts, your blower is going to run at about 50%. And this kind of explains why when you disconnect this low voltage, the fan jumps to high speed. If you drop the difference between the two wires to 0 volts, as far as the fan is concerned, you've asked for 100% power. And that's why when removing the plug, the low voltage, it should jump to high speed because as far as the blower is concerned, you've asked it to go full tilt. So we've got another slide on this, actually another couple. So this is a wire harness off a TFT, just as an example. So you can see the ground, the PWM is the variable voltage. We use, when we measure it in the field, we measure it with a zero, like a DC voltage on our voltmeters. Technically speaking, it's a PWM signal, which is pulse width modulation. And we won't get into that today, but basically pulse width modulation is you're turning on and off a voltage signal very, very fast, in this case around 20 or 30,000 times per second. And what our voltmeters end up seeing is they average the voltage. So if the power's on 50% of the time and it's going from 30 to 0, 50, 20,000 times a second, your voltmeter is going to average that out for you, and it's going to show you 15 volts as an example. So what we do we get you to measure in the field, we'll get you to go between black and red. You measure the difference between these with your voltmeter set to DC volts. And if you have a SOLA control, for example, and let's go to the next slide and we'll show you how this works, I hope. Okay, so TFT LX, any SOLA control boiler. So we're going to start off our blowers in the off position. The first thing that happens is so the control is the boiler's off. There's 30 volts on one wire and 0 volts on the second wire. So there's our 30 volts flashing there. And now our control wants to start the fan. So what it does is it applies 15 volts, in this case, to the black wire, and it waits for the feedback. So if 15 volts should be a 50%, but based on the pulse that comes back from that feedback wire, that's the dashed line on the right there, if the pulse is fast enough, then we don't change anything. But if the pulse was slower than the controller wanted, basically it would apply less or more voltage to get that pulse to where it wants to see it. So our controller adjusts the voltage up and down. So we go to 28 and then to 8 volts DC. And after we go to 8 volts, you can see that the pulses are much slower, indicating a much lower speed coming from the blower. So that's how your blower works. The colors of these wires it's going to vary. The feedback wire, your voltmeters just aren't equipped to read it. If you do happen to have an oscilloscope, you actually could hook it up and you could get a reading from that. For the rest of us, which is like 99%. Yeah, no, these days though, you can get a pretty cheap one for your phone. Yeah, you can get little plug-in ones with a little wand and they'll use your phone as a screen. So we've got a 30-year-old one at work that I play with from time to time. I barely know how to use it, but for fun, I was able to eventually get to read that feedback signal one day and show the tech guys, but it took me an hour to figure out how to use it. So it's not something I'd recommend you go out and buy unless you're interested in electronics as a hobby. Okay, so now we're on to our domestic hot water flow switch. So in the previous poll, we talked about magnets. So in a flow switch, basically they're really simple. The magnet gets pushed, it sits in like a plastic housing of some sort. As the water moves through the pipe, the magnet will compress some sort of very fine spring. Once the magnet moves underneath of the reed switch, the switch closes. So, and it literally is, if you were to put a magnifying glass on there, the reed switch doesn't look all too different to what I show here. It's just two pieces of iron wire. One sits on top of the other. There's a slight bend in one of them so that they don't touch, and then when you stick the magnet under, they do touch. So the flow switch is very basic. This is an old TI series flow switch. In this, where the two red wires go epoxied in there is a reed switch. In the newer boilers, so this is your TRX 150 Combi, 110 Combi, the GF 150 as well. You have two parts to this. This is the flow switch cap. Sorry, Steve?
No, it was me. I said Sean does a video with that.
Yeah, we actually just, Sean and Sean did a video about replacing this, I think, checking it.
But yeah, it's pretty cool.
So this piece here is the magnet rides up and down inside here. There's a filter at the bottom to keep large debris from getting into the flow switch. And on the dry side, so on the new boilers, we actually separated it out into two pieces. The reed switch is held in this little glass tube here, and there's two little metal contacts. So one way you can test these is if you have a magnet in your toolbox, hold it next to the reed switch. So these reed switches can be just pulled out of the boiler. You just tug on the wires, the whole switch comes out. If you stick a magnet next to it and your boiler activates for domestic, it means the reed switch works. And for some reason, the magnet that's in here is jammed up or it's not getting pushed. And of course, if you stick a magnet next to this and nothing happens, there's a good chance that the reed switch is damaged or broken. Haven't seen too many of those unless they get wet, but it does seem to happen. The magnets themselves, not much happens to them, although they are susceptible to magnetic debris in your system. So if you've got magnetite, that kind of thing, that can be a problem for these because it'll bind them up and they stop working once they get dirty enough.
And Dave, the other thing is they have to, guys, you want to service that switch every year when you do a preventive maintenance. If you could pop it open, check it, clean it off. I've pulled them and seen crap in the bottom of them. So, and that's just a preventive maintenance to prevent that thing from locking out.
Yeah, and this, you won't get any error codes if this fails. So there won't be any, it just, all that'll happen is you'll turn on the tap and just nothing. You don't get hot water. So next up here, we've got an electronic low water cutoff. I've chosen the one that goes in the NTI boiler because we're NTI and that's what we're training tonight. If you have a guard dog or something, it may run off of 110 volt power, but the concept is the same. So with ours, we've got a blue and a red, which supplies voltage to drive the machine and allow it to work the electronics inside. There's a switch contact, and on our boilers, I believe we still use just the 2 yellow wires. So if you see the 2 yellow wires on the low water cutoff, at least on the TFT and the LX series, sorry, TFT series, I should say, we don't use it on the LX. You can actually jumper the 2 yellows if you think you have a bad low water cutoff. And the way these guys work is the probe that sticks out into the water, it's charged. It's got an electrical charge to it. And then when you add water to the system, basically what happens is that electrical charge gets grounded out to the piping. And when the low water cutoff sees that the probe is shorted out to ground, it closes the contact and our safety circuit works. And that's why every 5 years we require that you take this thing out and clean this probe. The reason you're cleaning it is not to prevent like a false trip. Our actual main concern is that by cleaning this is you're preventing we don't want to get a false positive, meaning that if you get enough debris on this, the debris can actually build up on this metal, touch the steel piping of the boiler and short the probe out. And even though there's no water in the system and it's just crud, the low water cutoff may allow the boiler to fire without water if it's not cleaned. So that's why you have to clean them once every 5 years. It's not to prevent them operating, I guess, or to make it so that they don't trip accidentally. It's actually to make it so that they don't give you a false positive and stay working when they shouldn't. But yeah, that's how they work. And if you're testing one of these, you hold it in your hand. If you touch this metal tip to the boiler casing, the ground, it'll activate. The boiler will think there's water and it'll attempt to fire. So obviously you don't want to do that because bad things can happen. But if you have a spare one in your toolbox and you're doing some testing, make sure the boiler's full of water, plug it in, touch it to ground. If your boiler fires up and runs, you may have just diagnosed a bad low water cutoff.
And something you just brought up, pulling it every 5 years. Now that's something they put in their service contract. They can go in, listen, we come in and do a preventive maintenance. We're looking at your safety limits. We pull it out, we service it. It's not hard. It takes, a couple seconds to pull it out. It's kind of makes sense. Unless somebody puts blue lock on it or something, that's different.
Well, from the factory, we just use the yellow Teflon tape, so it shouldn't be too big a problem.
Yeah. If it's been out in the field for a while, somebody's done that, you always get that one guy who likes to use blue lock. But that is a good point because when they go out there, they should look at that. That's a safety. What did it make you do when you do an inspection on a commercial boiler? Make it go through all the safeties.
No, and it's an important one. So, all right. So the other thing we use a lot is thermal switches. So most thermal switches use a bimetallic or a strip or a bimetallic disc. And these work basically, there's 2 different types of metals that are glued or sandwiched together or bonded together. And as you heat them, we all know that things expand when they get hot and they contract when they get cold. Well, bimetallic strips are designed so that one side expands or contracts faster than the other. And basically the way they work is there's these 2 little metal strips, you add some heat, and eventually the side that expands more, so in this case the dark gray, opens the contacts and trips the thing open. Mostly these are resettable and they're either automatic. If it's a snap disc, it's probably a manual reset, meaning you have to manually pop it back to make it work again. Most of the rest of them that don't have a button or anything, they're automatic reset, which means that as soon as they get cold enough, they start working again. And if you go buy a really cheap electric baseboard thermostat, this is how they work. It's a calibrated bimetallic strip. I've got a couple of Honeywell ones in my house. They seem to work just fine. Very simple. I think they were $15 or $20. And anyways, they're just a bimetallic strip, and in this case, they run an electric baseboard heater. But yeah, that's how a bimetal strip works. Where do we use those? The Matrix Freeze Stat is a bimetal strip, except it's one that's designed to read cold rather than hot. T-Series safety limit, these were a snap disc and manual reset. TI Series manifold high limit. The TI Series, that actually should say stack limit, but anyways, that would be a stack limit there. And the only place we use it on the new boilers is on the burner door. And the reason we've gone away from bimetal strips to the extent possible is they're generally not as accurate or reliable as temperature sensors. So they're a little bit more prone to failure, especially if it's designed to be an operating limit, which means that every time the burner fires, it moves back and forth. Anything that moves has a limited life cycle count. And these were pretty high. I mean, they were probably 500,000 cycles, but certainly they would wear out more quickly than thermistors, which is what we're going to talk about next. So there's our wiring circuit. Now, a lot of times when we use these, we wire them in series with other safeties, which means that we go from one to the next, to the next, to the next. So if you've got a series circuit like this, the way to do it is, or the way to test it is to jumper it out one at a time. So you put a jumper across each switch individually, move on to the next switch, and in some cases you can bypass all of them for the purpose of troubleshooting only. Never leave your jumpers on. Thermal fuses, we don't have very many of these, which is a good thing because fuses are one and done. And literally the little bit of red here is made out of some sort of tin, or it's a metal basically. And when it gets too hot, it simply melts. So once you destroy a fuse, just like an electrical fuse, it's the same principle. It just works on heat. Gets too hot, you melt the fuse, and you have to fix the problem. So shown in the picture here is the thermal fuse that's on the back of a LX 300 up through 800. Again, if these trip, it's a very serious indication. Something's probably gone pretty badly wrong for these to trip, because they trip at like 350 degrees. So
Oh, my notes.
it's, yeah, you got to get them really hot.
That's like that TI burner, the top of the door you said burn up. It had to get pretty hot.
Yeah, we added a snap disc. We didn't put a thermal fuse on, but we added a snap disc to those. Yeah, so temperature sensors. So there's a bunch of different types out there that you guys will have come in contact with. Negative temperature coefficient thermistors is the most common thing, like by far. They're insanely cheap, they're insanely reliable, and they're basically used everywhere. There's other ones called resistance temperature detectors. The lab would use some of those. Thermocouples, which I've got the symbol for each of these. So there's a thermistor symbol at the top, electrically speaking. Resistance temperature detector would be depicted like the center symbol here. Thermocouple would be the one at the bottom. And then there's semiconductor-based sensors. The thing with semiconductor-based sensors is you don't see them because they're embedded in a microchip, so they're kind of more for information's sake. Thermocouples, you probably got one with your voltmeter. It's two dissimilar metals, and when you heat those metals, electrons move from one piece of metal to the other, and you get an electric charge that your voltmeter reads. The ones we're going to concentrate on for the most part are these thermistors, because that's basically all we use. So there's a resistance chart for a typical 10K thermistor. They call it negative temperature coefficient because as our temperature rises along the bottom, the resistance falls. So the two are doing opposite things to each other. And as our temperature falls or gets colder, the resistance goes up. And it's going to create a curve, something like what you see there. Don't worry about this. If you Google 10K thermistor, you can get this resistance chart basically anywhere on Google. It's also in every manual, and you can use this as a comparison to test your thermistors and see if the reading you get on the screen seems valid. The other thing you can do is use your hands. most of you guys will touch a pipe and within 10 or 15 degrees, you can probably tell me how hot it is. If you've got a bad sensor, it's usually so far bad that you can touch the pipe and the boiler says it's 200. Well, we know that's probably wrong. So, you know, trust your hands and look at the readings that you see on the screen. These come in all shapes and sizes. There's no, basically the bit that you actually sense with is this little tiny pip right at the very end of this one in the bottom here. And embedded in these brass and stainless and plastic and whatever housings, these are all 10K sensors, all different shapes and sizes. They all do exactly the same thing. And the actual sensing element is exactly the same on all of them, just different applications, so they get different housings. So there's a 10K output table. So you can see as the temperature gets warmer, so as we go from -39 to +35, you can see that the resistance value changes pretty dramatically. Okay, we're going to talk a little bit about flame rods and flame rectification. All right, guys, so this is your basic flame rod. It's basically consists of 3 parts. You got a mounting flange, a canthal, which is the metal that this rod is made out of, and this rod runs continuously from top to bottom. The purpose of the rod is to conduct electricity. The purpose of the ceramic insulator is to isolate the rod from anything that it might touch that could be electrically conductive. So look for cracks in that ceramic. If there's cracks in it, give you lots of problems. Now, to understand how a flame rod works, we're going to very briefly go over AC versus DC power. So DC means direct current, AC means alternating current. And I got a couple little demos here. So you can see an alternating current generator here, and you see the little green electrons going backwards and forwards. That's an alternating current. You see our typical sine wave graph on the right here. And this graph is representing the voltage. So the voltage goes positive, the voltage goes negative over and over. And I actually found this one here, which I thought was neat because a lot of times I use analogies to water piping for electricity. Well, here's an alternating current pump, I guess, in a water channel, but you can sort of see what happens to the water. The water just goes back and forth, back and forth. So that's what alternating current means. Direct current is one continuous direction. So one is a river, one is a wave pool. Okay, so now we get on to AC/DC flame rectification and my favorite band. So for those about to rock at Troubleshooting, we're going to go over some flame signal. So we call it flame rectification because the flame rod actually takes this AC signal. So our current goes to the right, I guess, as the voltage increases. As the voltage decreases, the current goes to the left and back and forth. And so this will happen over and over again. I don't remember how long this slide goes on for. There we go, not too long. And what our flame rod does to this AC power, or this AC current, is it rectifies it. And what rectification means is it takes an AC voltage and turns it into a DC voltage. And what the DC voltage means is instead of going up and down anymore, it turns it into a straight line. So it becomes +5 volts or +10 volts or whatever it becomes. It's a single voltage signal. And the way this occurs is we apply AC voltage to our flame rod. So there's our flame rod. It sits in the flame that comes from the burner, and the burner is actually just a ground, an electrical ground. And so here's my handiwork. I know Bob Ross has got nothing on me. So as our voltage goes negative, for this example, the electrons will jump out of the flame rod and they actually conduct through the flame. The flame is like a piece of wire, and then they shoot out and they hit and they stick to the burner. Basically, the electricity always wants to go to ground. So electrons come out, they go to ground. Now, what happens when the voltage goes positive or goes the opposite direction is all of the electrons stick to the burner because the chemical nature of the flame means that electricity cannot conduct backwards through it. So it's fairly good at conducting electricity down. It doesn't do such a good job at conducting it back up. And so what happens is your controller is monitoring this voltage. and these electrons, and it knows that it sent, for example, 100 electrons out, and it only got 90 electrons back. So the difference between 90 and 100 is 10. So that means the flame signal is 10 microamps, or so is typically how we would measure it. So let's jump through this. And the reason we do this rather than just putting a thermocouple or something else is if there's no flame, there's no conductivity. So that means we don't get any electricity forward or backwards. So there's no flame signal. If our flame rod happens to be touching the burner, what's going to happen is all the electrons will exit to the burner. And because of metal on metal contact is it conducts both ways equally, we get all the electrons that we sent out back. So we sent out 100, we get 100 back. The difference between 100 and 100 is 0. So we've got 0 flame signal. So that's the symbol you want on your voltmeter. You don't have to spend a lot of money to get it. It's the symbol for microamps. Don't get confused with this guy here, MA. Over the years, I've talked to hundreds of guys that are saying, "Oh yeah, no, I've got MA, it's working." 1 milliamp, which is the MA, is 1,000 microamps. So 1 amp is equal to 1,000,000 microamps. So if you have MA, that's 1,000 times too big. So how does our flame affect our flame signal? Well, the flame is the electrical wire. So small flame, just like having a small wire, can't conduct very much electricity. And what ends up happening is you get a small flame signal. If you have a big flame or a healthy flame, it means that you've got a bigger electrical conductor, which means more flame signal, more electrons move back and forth. So that's why every time you call tech support with a flame proofing problem, we're making you break out your analyzer and check the venting, check the combustion, all that. We're not doing it to be annoying. It's because a good flame means a good flame signal, and it's not a pass fail as such. It's a qualitative measurement. Okay, we're going to skip over that. I don't remember why it's in there. Okay, so I've got a couple of just basic troubleshooting slides for these are directed to TRX FTVM products only. So we're going to go over the sort of the 4 or 5 most common error codes. So first thing, if you get an error 101 code, and especially if you do not get any overheating, you want to inspect this electrical connector here. And I apologize, the photo sucks. There's 2 little black wires that come off here. They're designed to go to an external safety limit. If they've been cut or used for low water cutoff or whatever, check those. If that low water cutoff is tripped, you're instantly going to get a 101 before the burner even fires. If you have a Series 2, so you've got the new blue and display with the dial on it, the Series 2 boilers take these 2 electrical wires and they go up to the burner door limit. So if that burner door limit trips, you're going to get a 101. Now, the 101 actually means 2 different things. The second thing it means, and the more common one, is that your boiler has overheated in some fashion. So I've grouped together 101 to 105 because they're all basically the same thing. They mean something got too hot. There is a slight variation between them, but realistically it means they got too hot. So you want to make sure all the air is purged. You're going to check your supply and return sensors for water damage. If those sensors get wet, they become more conductive and the boiler's going to read the wrong temperature. Check the return filter on the TRX 85 to 120 and the 150 combi. It's built into the boiler. It often gets plugged with debris if you've got a water quality issue. Disassemble and clean the pump. This is the #1 problem for this error code. So you take the pump out, you pull this impeller out, clean the magnet, clean the rotor, make sure there's no junk in there. Check for the blue pump on the light, make sure you've got power to the pump and, diagnose if you don't have power, why that would be. On new startups, if you're not using the domestic, or even if you are using it, watch that diverting valve. Sometimes it gets locked in the wrong position due to pressure differences, due to air locks and things like that. Make sure the diverter valve is working, and also, again, if you're not using the diverter valve, make sure you've disabled it correctly, because if you don't, you could be deadheading your boiler pump. So 301 to 307, this is like an internal PCB fault. Any internal fault on any boiler from any manufacturer, you should always start by doing the same couple of things. First thing you're going to want to do is line to ground, line to neutral, neutral to ground. If you do not get these readings, or like 110, 115 volts, and you get like 50 volts to ground on neutral or something, fix your power first. Second thing you want to do, remove any and all low voltage wiring. Get rid of the thermostats, the tank sensors, the system sensors, anything that's got a low voltage that's connected to the boiler, remove them all. And you're doing this to simplify the situation. If your problem goes away when you remove all that stuff, I would say the odds are better than average that your problem lies in the system wiring. We have had boilers in the past where people have wired by accident, domestic hot water to thermostat. Instantly, you get an internal fault on the boiler control, and as soon as you remove the wires, the problem goes away. Sometimes it's easy to do. Sometimes the terminal strips are hard to read. The boiler rooms are not well lit. Carefully inspect the low water pressure switch, and this is specifically to do with TRX FTVN boilers. If that pressure switch or the wires get wet or damaged, it very commonly causes a 303 error code, and once you dry the wires off, your boiler control is perfectly fine. You don't have an issue. Look for water damage, and of course, water damage is as soon as you get something wet, all bets are off. Just a couple more slides, guys. Error 309 or 502, flame detected out of sequence. I apologize if you have an older TRX FTVN installation manual. Error 309 said something about a gas valve relay safety check failed. Realistically, the code means that your flame rod is shorted out because it's cracked or damaged or wet. Make sure the combustion chamber is dry, make sure the rod's in good condition. And I've put here, it's never the PCB 99%, which means that for a 309 502, it's essentially never the PCB. It's like always the flame rod. But I guess there is a 1% chance that it could be a PCB, but I would never start there. Okay, we're going to go through next 501 to 504. This is 501 is no ignition. 504 is a flame loss during a run, but really the only difference between these two is if you have a 504, you know the igniter works, but everything else is the same. So your intake and exhaust must be clean and clear. Check for your gas pressures. Don't assume that they're good. I can't tell you how many times I've talked to a guy and he said, oh yeah, my gas pressure is like 8 inches. And I'm like, yeah, but when did you check it? Well, last year when we installed it. Don't care what it was last year. We need to know what it was today, preferably the 30 seconds before you call tech support. So we've got test ports. Look for this kind of stuff. I mean, if you see this, there's obviously a problem. One that's a little less obvious though, pull out these Venturi inserts, and if you look, there's just a tiny bit of white corrosion in there. That's enough to actually choke the gas flow in the boiler to where it won't stay running anymore. So anything that's got a flapper Venturi, pull it out, inspect the orifices. Okay, we've got two little test ports for testing your gas pressure. They are there for a reason. It's because we do want you to check it every time you do a combustion test, and especially when troubleshooting. Check the gas orifices for any boilers with dual Venturis. And don't be afraid to take apart the burner. Take this piece to the kitchen sink, wash it. They do get plugged up over time. You guys all have a shop vac, so you know that over time you suck in all the dirt, it sticks to the filter. Well, the boiler's a shop vac in reverse. We blow all the clean air into the center of the filter, which happens to be your burner, and all the clean air comes out and all the dirt stays inside. So they can and do get plugged up.
Airflow, number one.
Okay, check your igniters. So 3/16 gap is pretty typical. Use an Allen key to measure it. Look for warps, twists, bends, cracking. And if your boiler's lighting and running intermittently, make sure you check that combustion. It has a very big impact on how well your boiler's going to work.
2 US nickels stacked together will be 3/16.
Yeah. So remember the Boy Scout rule. You need heat, fuel, and oxygen, or fuel, air, spark to have a flame. But the difference between the Boy Scouts and the boiler, and this is one thing I teach, this really should be, for the boiler world, this should be a fire square, because the one thing it leaves out is flame signal. I always ask my new trainees and recruits, and I'll say, when do you stop building a campfire? And nobody ever has an answer to it because they don't even realize what they're doing. But the answer is you stop building your campfire when you see smoke and flame and whatever, because that's flame signal. Well, the boiler sees flame signal via the flame rod. It may be burning perfectly, but if it doesn't see the flame, it doesn't matter. It's going to shut down. So when you have a boiler, you need that flame signal. So really it's a fire square when it's a boiler, because you have to have flame signal. As humans, we don't recognize it as anything special because we just do it automatically. Once our fingers start burning, we kind of realize that it's lit. We see the flame, we can smell it, whatever. The boiler only has one sense, and that's the rod. If that doesn't work, nothing else really matters. 612 fan. So this is a fan speed proving error code. So first thing you want to ask yourself is, does the fan start? So if you can hear it starting and running, yeah. If you don't hear it starting and running, find this low voltage connector, remove it. The fan should immediately jump to high speed. If it does not, make sure you've got 120 volt power and you don't have a blown fuse. And I would say 9 times out of 10, what you're going to find is you got a bad fan. You have to replace it. So that one's the easy one. The hard one is when the fan appears to work, at least sometimes, and you get intermittent 612s. Now, I will say, in my experience in tech support, 90% of the time, intermittent 612s, especially on the TRX FTVN, it's going to be a fan harness issue. The other 10% of the time, it's probably the fan, and maybe 1 out of 1,000 times is it a boiler control. So, our control is going to fire up. Always, at very least, check for this voltage. So you want to have a look at this harness here. If you see no voltage on any of these wires, and you can just measure each one to ground, and your fan seems to run, like when you remove the low voltage, it could indicate that you have a control problem. It's exceptionally rare, so I almost hesitate to mention it. So the control is like never your problem, or almost never. But at very least, measure the voltage to ground. You should, on any blower that's variable speed, find 2 wires that will have, one will have a fixed voltage like this, 30 volts, and you're going to have one that really you can't get any reading on, and one that's a ground. And the one that we didn't talk about is the variable voltage. At very least, you should see that voltage change. So on this blower, you would measure between red and black. And even if you knew nothing about the blower, what you should see is when you give this boiler a call for heat, you should see a change in voltage, and the blower should respond to that change in voltage. If there is no change in voltage, it means your controller didn't turn the blower on. If you do get a change in voltage and the blower does not start, it means your blower is not working, and I have seen that happen. There's an electronic failure on the circuit board that can happen where it'll run full speed, but it can't run at 50%. It has no in between. It's kind of on or off. So that is a failure that can happen with a blower. But most of the time, it's a damaged harness. So that's where I would start. And that's pretty much it for me, guys. Sorry I ran a little bit long there, but that's what I've got for you tonight.